Every single day, somewhere in the world, a commercial airplane gets struck by lightning. Not occasionally, not rarely, every day. In fact, the average commercial aircraft gets hit by lightning once per year. And most of the time, the passengers never even know it happened. A bolt carrying up to 1 billion volts of electricity hits a metal tube doing 900 kilometers per hour at 12,000 meters, and everyone just keeps watching their in-flight movie. How is that even possible? The answer involves one of the most elegant engineering tricks in aviation, and it rewires everything you think you know about electricity. Let's set the stage. A single lightning bolt releases around 5 billion joules of energy. That's enough to power a house for a month, discharged in about 30 microseconds. The temperature of a lightning channel? Roughly 30,000 Kelvin. That's 5 times hotter than the surface of the sun. Now picture that hitting an aircraft moving faster than a bullet train, packed with 300 people, full of jet fuel, electronics, and pressurized air. By every instinct you have, that plane should be gone. But here's the thing. It's not the bolt that engineers had to solve. It's the path. For the first few decades of aviation, lightning was genuinely terrifying. In 1963, Pan Am Flight 214, a Boeing 707, was struck by lightning over Maryland. The bolt ignited fuel vapors venting from the wing tank. The plane went down. All 81 people on board were killed. That crash changed everything. The FAA immediately overhauled fuel tank venting standards. Engineers started asking a question they'd never asked seriously before. What actually happens when lightning hits a plane, and how do we control it? They discovered something profound. The danger isn't the lightning itself. It's where it enters, where it travels, and where it exits. Control the path, control the outcome. And that realization launched an entirely new field of aircraft design. Here's the fundamental principle, and it's surprisingly simple. Lightning doesn't care about your plane. It's just looking for the fastest path between 2 points, usually cloud to ground or cloud to cloud. Your aircraft just happens to be in the way. So engineers stopped trying to block lightning, which is impossible, and started doing something smarter. They designed the plane to conduct it safely, completely, from one end to the other, without touching anything critical. Think of it like a river. You don't stop the flood. You build the right channels. Here's how it works in practice. The fuselage of a modern aircraft is essentially a giant conductor. The aluminum skin is thick enough and continuous enough that when lightning strikes, typically at a nose, wingtip, or tail, the current flows around the outside of the aircraft like water over a stone. This is the same principle as a Faraday cage. The electricity travels through the conductive shell, completely bypassing the interior. The passengers inside? They're sitting in a protective bubble of metal. But here's the interesting part. Modern aircraft use more and more carbon fiber composite materials, like the Boeing 787 Dreamliner. Carbon fiber is conductive, but not nearly as conductive as aluminum. So engineers embed fine copper or aluminum mesh directly into the composite panels. Invisible layers of metallic webbing that give the lightning a proper highway to follow. Now picture this. The bolt enters at the nose, races along the fuselage skin at nearly the speed of light, and exits at the tail or a wingtip, all within microseconds. The aircraft barely flinches. But that's not the full story. The real engineering challenge isn't the fuselage. It's everything inside it. When billions of volts race along the outside of the plane, the rapidly changing electromagnetic field induces voltage spikes inside the aircraft, in the wiring, avionics, and flight computers. Think of it like a transformer. The outside current creates a magnetic pulse that reaches through the skin and into the electronics. So every critical wire on an aircraft is shielded, twisted in pairs to cancel magnetic fields, routed away from the fuselage skin, and protected by surge suppressors. The avionics are hardened against electromagnetic pulses. There are redundant systems for every critical function. The plane doesn't just survive the strike. It's built for it. Here's something most people don't know. Aircraft don't just get struck by lightning from storm clouds above. Sometimes they create the lightning themselves. A plane flying through a highly charged cloud can actually trigger a strike. The aircraft acts as the initial conductor, connecting two regions of charge that wouldn't have discharge on their own. It's called a triggered lightning event, and it accounts for a significant portion of all aircraft strikes. Here's another one. Before any new aircraft design is certified, it has to pass a direct lightning attachment test. Engineers literally shoot artificial lightning at the aircraft up to 200,000 amps in a controlled lab, mapping every entry and exit point to ensure the current flows exactly where it's supposed to. They call these points lightning attachment zones, and they're color-coded on engineering diagrams. Zone 1 is where strikes are most likely. Zone 3 is where they're least likely. Every inch of the aircraft is categorized before it ever sees a real storm. And finally, those static discharge wicks you see on the trailing edges of wings and tail surfaces, the thin black rods pointing backward, they bleed off static electricity the aircraft accumulates during flight, reducing the voltage differential that makes strikes more likely in the first place. Tiny rods. Enormous job. Here's the real insight. We've spent a century trying to make aircraft avoid the most violent forces in nature. But the deeper lesson from lightning engineering is different. You can't avoid everything. Some forces are simply too big, too random, too inevitable. The smarter move is to understand the path and design around it. Give the danger somewhere to go. Build the channel. Protect what matters. Every time a plane lands safely after a lightning strike, it's not luck. It's the result of decades of hard lessons, quiet engineering, and a philosophy that sounds almost like wisdom. Work with nature, not against it. Now, if you think lightning strikes are wild, consider this. What happens when both engines on a commercial aircraft flame out completely at 40,000 feet? It's happened more than once. And the way pilots brought those planes down safely will make your jaw drop. That story is next. Subscribe so you don't miss out.